Okay, I started the video again because I want to do like one page at a time. So in this case, here we have definitions on top of page 2. A function is continuous in an interval if and only if it's continuous at every point in that interval, okay? And it's continuous if and only if it's continuous at every point in its domain, which we saw. So we have to be very mindful about the words we use. So here we have 1 over x, which I know looks like this, and which I know x cannot equal 0. So our domain, of course, is that. Actually, I'll do it right here. I don't know why I did a bracket, it makes no sense. Ah, geez, come on. There we go, parentheses. Now, is this function continuous on all real numbers? Well, of course not. There's a break at x equals 0, where we have a vertical asymptote, which, by the way, we call an infinite discontinuity. And we're going to talk about that often in this section here. But the domain here is actually negative infinity to 0, and from 0 to infinity, non-inclusive for 0. Is it a continuous function? Yes, because it's continuous for its domain. So the answer is yes for that one. Let's look at another example. The greatest integer function, which we did discuss, I think in a homework assignment not too long ago. And it's a step function. To remember the way this works is if I plug in 0.1, I get 0. The greatest integer less than or equal to the input. If I plug in 0.9, I also get 0. But once I do 1, then I get 1. Or I do 1.1, I get 1. Then I get 2, and so forth. So we also call it a step function too sometimes. They look like steps of a staircase. Is this continuous on negative infinity to infinity? Well, of course not. We have all these breaks here, right? I have to lift the pencil or lift my finger off the left mouse button to draw this. The domain is all real numbers too, because I can plug anything I want here. So this is not a continuous function. So sometimes you get those unique or rare cases where a function would not be continuous because there's somewhere in its domain that's a problem. For example, it's not continuous at x equals 1. Because f of 1, of course, equal to 1. But the limit as x approached 1 did not, of f of x, or g of x, I guess, did not exist. Because your LHL and RHL were different, right? So that's what's happening there. Let's keep moving. Example 4, and then we're going to have a little discussion about these at the bottom here. Let's look at a piecewise function, and without sketching, then I'll sketch afterwards, determine analytically whether it's continuous at x equals 1. Does f of 1 exist? So is it defined? Well, of course it is. And what is it? You're going to use that expression. So we're good. That's condition 1. Condition 2. Does the limit exist? So is the limit as x approaches 1 of f of x exist? Well, you got to find the LHL and RHL. LHL, left-hand limit. The limit as x approaches 1 from the left of f of x. Well, if I approach 1 from the left, I got to use this one, which of course is 2. My RHL, the limit as x approaches 1 from the right of f of x, 5 times 1 minus 3. So when x is a little bit bigger than 1, like 1.001, whereas the left hand like 0.9999, whatever, minus 3. Let me do it a little more neatly. Yeah, they both equal the same thing, so that exists. And then the third condition. Does f of 1 equal the limit as x approaches 1? Well, of course, they both equal 2. So the answer is yes again. Now, what would happen for this to not be continuous? What if I didn't have an equal sign here? And what if I had a random number like 4 at x equals 1? So f of 1 would have existed, it would have been 4. The limit would have existed as still 2. But then f of 1 and the limit as x approached 1 were different things. And that would have been a hole. And graphically, it would have looked like this. If I had a little revision here where I had 4 in the middle. But since I did not, and 1 was included, then the hole actually fills in that, the point fills in that gap, and then I'm continuous. I don't have to lift the pencil off the paper. So example 4, the answer is yes. Because all 3 conditions were met. Okay, let's clear the drawings. Now, types of discontinuities. This is fun. We could have removable. Which actually are both of these cases here. You could have a jump, which is this one right here. You could have an infinite discontinuity, which is a vertical asymptote, like that one. Or you could have an oscillating discontinuity. It's not necessarily a break, so maybe I shouldn't call it discontinuity. Well, but the problem is that we can't really get a clear picture of what's happening at x equals 0 because we can't plug in 0, and it just does this really weird stuff as I get close to it. So those are our types of discontinuities. Now, here, f of c did not exist, if you call this point C here. So condition 1 failed. So you just stop and say it's not continuous. Here, FC did exist for the second graph from the left. Here, my limit also exists. But then condition 3 failed. Because the limit did not equal f of c. So when you have removal discontinuities, removal meaning you're removing a point. You remove a point. Either you remove a point completely, like it did in the far left, or you remove it and put it somewhere else, like in the second graph. Regardless, as you go through the checklist, it's going to fail somewhere along the way. In the case of the far left, FC didn't even exist. In the case of here, if they call this x equals c, it's f of 1, f of c existed, the limit existed as x approaches c for f of x. However, f of c did not equal the limit as x approaches c. Let me clear because it's getting a little busy. Here we put c, and here we'll put c. Now here, does f of c exist? Well, yeah, of course. But condition 2 fails because the limit does not exist. That's because the left-hand limit and right-hand limit are not the same. Here, for x equals c, the limit also, well, first of all, f of c does not exist. But more specifically, what's happening, so of course, that fails, but more specifically, the limit as x approaches c from the left or from c from the right, if you ever get this happening, plus or minus infinity, that's going to be infinite discontinuity, which we know is a vertical asymptote. So you have to kind of know the specifics for why these things fail to label the discontinuity. And we're going to spend a lot of time talking about this on Tuesday. And this one here, kind of strange for the oscillating one again. Obviously, if you put c at x equals 0, f of c does not exist. And the limit also does not exist either. So you just have to kind of just just accept it for what it is. There's not really any formality to it as we have with the other ones. At least I'm not aware of any formalities for the oscillating ones. Okay, so that ends page 2 of the notes. So I'll stop the video and start one more.